Hello. Hello, welcome to my new live stream. So, the plan for today is to do what we didn't finish last time, which is to actually do the FAT32 and the FAT16 implementations in our little operating system that we're working on right here. Yeah, I hope you can hear me well. I hope that things will go better this time than they did last time. So yeah, let's get started and see what happens. Okay, so if you remember a couple of live streams ago, maybe 2 live streams ago, we had some trouble with actually when we started to integrate this hard drive functionality. So to boot from a hard disk image, the box debugger stopped working. And, you know, I've been trying to figure out why that happens, and I kind of found it. And I would like to share my findings, because I think this is kind of interesting. And as always, when I'm doing this type of stuff, I'm trying to explain, not just to give the solution, but to also explain how I got there, how it works, how I got there. Okay, so this is the code that is from... So the only thing I have changed here is I've added a couple of comments here in the linker ALD in stage 1 to make it easier to understand what is going on here. But for the rest, it's the code from this bootloader 2.0 branch. We can find it on GitHub. Okay, so let's see what's going on. Scans debug. In the last video, we moved from make files to scans. Okay, so okay, this terminal is not working for me anymore. No idea why. All right. Okay, now in my installation, it looks like in Fedora the default box, it works a bit differently. So to get the actual debugger in Fedora, you need to use not box, but you need to use box debugger. So I'm gonna change that, but I'm not gonna commit it to... Alright, so scripts, box. And we have to use the box debugger, and there are a couple of more options. So -q is that so we don't get this prompt that... Okay, let's test this. Scans box. Okay, so it's complaining that the number of heads is set to 32, which is out of range. Okay, so let's set that heads number to something smaller that box is happy with. And also, since I reinstalled my operating system, these files don't exist anymore, so let me just fix those. Okay, these are the defaults, and they worked just fine for me, so I'm gonna leave them. Okay, and yeah, the number of heads, let's set it to something that it will accept, like 16, for example. All right, let's run box. Okay. Oh, okay, so I have this boot set twice, so let me just remove one of them. Okay. All right, so the problem that we encountered previously with box was that when creating a formatted disk, we are using parted. Parted is one of the tools that we can use to do that. And parted has installed a default MBR. And that default MBR is making some assumptions about the geometry of the disk. So let's see what it actually does. I'm gonna put a breakpoint at 7C00, which is when where the boot code starts. And let's go there. I'm just gonna step over until I get to that int13 hexadecimal. All right. And here it is, so I'm gonna stop. Okay, so what do we have here? Okay, so basically the way this works is, let me just open up a text file. So the way this int13 hexadecimal works is that in DH contains the head, and then CX is split into two parts. So let's just put whatever we have here. So in our case, the head is 0, 0, which are these two numbers. So we're trying to read from head 0. And for CX, the value we have is 1001. So let's write that here. And now I'm gonna convert this to binary, which would be 0001, 0000, 0000, 0001. So these are in hexadecimal, and I'm converting them to binary. Now what happens is basically like this. This is the sector number that this int13 hexadecimal takes, and this number is the cylinder, except that this little 00, it goes in the front like this. Okay, if we convert back to hex, this would be 1 and 0, so head. Okay, so we are trying to read cylinder 10 in hexadecimal, and this would be the sector, which would be 1, and then the head is 0. All right. We also looked last time at the binary, so let's look at that as well. I think it might help a bit. All right, so this is the raw image, and this is basically the MBR code that we are seeing that is being executed right here. And if we go down here, this portion is basically the MBR headers, which contain the information about all the partitions, how big they are, and that kind of thing. All right, so let's go to the article about MBR so we can figure out what we need to read from here. Okay, so the first partition table entry starts at address 1BE. So let's go there. 1BE would be this number. All right, and here the first byte is the drive attributes, and then the next 3 bytes are the CHS, so the cylinder head and sector, address of the partition start. And if we look here, guess what we see? So the head is 0, the first number is the head, and then we have 1001, which is exactly what we have here in CX. So what this MBR code is actually doing is just reading the stuff from the disk and just putting those into registers. Okay, then the next number is the partition type. Okay, let's skip over it. Then the next 3 bytes are the CHS address of the last partition. So basically, this is how we can figure out what the size is. Okay, and then we have the LBA of partition start. All right, so this is that partition type. This is where the partition ends, and then this is the LBA address. Okay, so LBA is 0x. We're reading from right to left because this is in little endian. So it's 8 and then 2 zeros, 800. All right, let's convert all of these numbers to decimal because they're easier to read. So this one is 0, this one is 16, and this one is 1. And 800 have this handy little tool. Is 2048. Okay, so what we have here is basically we know that the partition starts at this number, so at sector 2048. And we know that the CHS, let me put these into, is 16, 0, and 1. So this is the CHS number, and this is the LBA. And we're trying to figure out, okay, what is the geometry of this disk? So let's just use the formula for this. There was this article on Wikipedia, which had the CHS conversion. Okay, I think the article... Okay, here it is. So this is the formula. This is the magic formula. And let's plug this formula in and replace all the numbers. So we know what the LBA is. It's 2048 equals C, which is the cylinder, 16, multiplied by HPC. This is the number of heads. Okay, let's just say that here, that we're trying to figure out. Then we have H, which is the head. In our case, this is 0. And then multiplied by SPT, which is the number of sectors per track, or sectors. Plus, and then we have S minus 1. S is this sector, which is 1 minus 1. Let's replace all of these. Let's do all the calculations, and what we get is 2048 equals 16 times heads multiplied by sectors, and this is 0, so we can delete it. All right, let's divide 2048 by 16. Divided by 16 is 128. So what we have is 128 equals heads multiplied by sectors. So this is the assumption that is being made here, that the number of heads multiplied by the number of sectors is 128. So what combination of numbers could we have here? We could have, I don't know, for example, 2 heads and 64 sectors. We could have 4 heads and 32 sectors. And we can play with these numbers as much as we want. All right, so let's see what happens if we put these numbers into the box emulator here. All right, so I'm going to set the number of heads to 4 and the number of sectors per track to 32. Now, something that I noticed when doing this is that box will not do, this will not work properly unless we also add the cylinders. So if we don't specify the cylinders, then this will not work. And another thing here is, okay, let's go back a bit. Okay, I don't have that CX scheme, but let's put it back. So let's say that these are the bytes from CX, right? So we have, okay, we have 16 bits, sorry, 0000, 0001, I don't remember what it was, 00000001, okay, whatever, it doesn't matter. So if we split this here, you can see that we have 6 bits for the number of sectors. We have 6 bits, which means that the number of sectors cannot be any larger than 2 to the power of 6, which is 2 to the power of 6 is what is it, 16 or 32? Okay, it's 64, right. So this is the maximum number of sectors. So maximum number of sectors. And then for this number, we have 8 and then another 2. So we have 2 to the power of 10, which is 1024. So we have a maximum number of 1024 cylinders. And this is another thing that I found through trial and error. If we specify the number of cylinders which is any larger than this number, so 1025 for example, then box will not work. It's not going to be happy about this. And that's the thing, we are not seeing any errors here. It's just not working, it's not booting. But if I set this to... Okay, I need to close this nicely because it leaves a log file. Alright, if I set this to 1024 and then run box, now it works. Now it boots our image. Alright, which is great. Okay, so let's continue with the next topic. So we fixed box, we fixed whatever was wrong with box. Alright, now let's debug and see what is going on with whatever we had trouble with last time. So if you remember, last time we were having some issues with... So we basically started adding this support for booting from an MBR disk. We tried to find where the partition starts, and now we are trying to read that partition. And we're getting some issues. Some things are not working properly, and we need to figure out why. Okay, so let's just run and see what we've got. Alright, so what we get is read boot sector failed. No idea why this is happening, but let's try to figure it out. And the first thing I did was to try to figure out, okay, I was thinking that maybe the issue is with here in stage 2. Maybe the issue is with this gets drive parameters function. So I just went ahead and printed everything to see what is going on. Get drive params ID cylinders heads sectors. All right, and let's just copy all of these from here. Cylinders, sectors, and heads. Okay, and let's see what happens if we run with this. And okay, so we're getting 50 cylinders, 24 heads, and 2 sectors. This doesn't make much sense, because our image, we specified the size here, and yeah, we can check with, yeah, let's actually check. So stat build debug, okay, image.img. The image is 262 megabytes. If we add all of these up, so remember these are in hexadecimal. Let me just move the calculator. Okay, so we have cylinder 50, that's 80 multiplied by 24 heads multiplied by 2 sectors gives us this number. So if we multiply this by 512 bytes, we get what is this? 2 megabytes. This doesn't make any sense. This shouldn't be happening. So then I went ahead and looked at the code to see, okay, why is this happening? Is it a bug in Camo or is it a bug in my code? And then I saw this. So I'm calling the get drive parameters using the disk ID, but I'm only setting the disk ID here. So that was the problem. All right, if we fix this variable, then this issue goes away. All right, let's see what we got now. Okay, so now the numbers are a bit more reasonable, and we are seeing here that the cylinder is 3FF. Let's see, how much is 3FF? So 3FF is, here we go, 1023. And guess what the limit for the number of cylinders is? It's 1024, because it is limited to 10 bits. So essentially what is happening here is that Chemo is just giving us the highest number it can possibly give us. It's just giving us 1023. And unfortunately, what this means is that we cannot read the whole disk. What we can read is 3FF multiplied by 0x20 multiplied by 4 and then multiplied by 512. 64, around 64 megabytes. That's as much as we can read using this int13 hexadecimal. So essentially, Chemo is hard coding the number of sectors and the number of heads to 4 and 20. And there's nothing we can do to improve that. I think something is odd here. Yeah, these two are... I just inverted these two, because I thought the number of heads should be smaller. So it's 4 heads, 20 sectors per track. Okay. But we are still getting this read boot sector failed, which is odd. So now we should have the correct numbers here. Okay, so let's see what else is wrong here, because we obviously found a bug. There might be others. Okay, so, you know, in order to fix this, let's try to figure out what is actually ending up here in this read code. So x86 disk read. Alright, so what we're gonna do is I'm going to go to the stage 2 .map. Okay, why do I not have a map file? Okay, I do. And disk read starts at 2117. So let's take that and let's just use the debugger and try to figure out why this is not working. Okay. And let's add a breakpoint at address, whatever this number is, and continue. Continue, continue. Okay, so now we are in this function. Okay, let me just put them... Okay, so we are in disk read. And let's keep all the way to this int13 hexadecimal. We don't care about anything else. What we care about is seeing what numbers are being passed to that interrupt. So we can see that the interrupt is called at 2136. So let's just put a breakpoint there. 2136 and continue. And now let's print all the registers. Okay. So, we are getting... Let's write this down. So, CX is 1. Okay, and DH, where is DH? DH is here. DH is 0 because okay, so this is DL basically. The lower two digits are just DL. Okay, so DH is 0. All right. So we are trying to read the first sector, and I think this makes sense. Let's see if we break this down into binary. We get 0, 0, 0, 0, 0, 0, 0, 0, lots of zeros, and then finally a 1. And if we split this in two, this is the cylinder, which is 0, and this is the sector, which is 1. And this is the odd thing about this CHS scheme, is that all the, the cylinder starts from 0, the head starts from 0, but the sector starts from 1. So yeah, this looks correct. Okay, let's check the other parameters. Let's see what we need to pass. So int 13h, read sectors from drive. Alright, so DL should contain a drive. Let's see, we have the drive in DL. And DL is 53. Why is DL 53? This is weird. Are we reading from the wrong drive? Because I would expect it to be 80. Because the disk is usually mapped to 80. And this number is certainly weird. So let's see what we have here. And this problem started happening when I added the partition stuff. So let's check the code again. And this is where I found that, okay, inside this partition structure, I have the disk and then the partition offset and partition size. And guess what? I'm not setting the disk anywhere. And yeah, that's kind of how I found this issue. I started looking at all the code, trying to figure out, okay, what am I doing wrong? So part disk equals disk. Because this, seeing that this number is wrong here indicates to me that something is very fishy. Something is fishy here. Maybe something isn't passed correctly. And I started tracing, where this call is coming from. So it was disk read sectors, which I know works. And then we get here to this partition read sectors, which is when I'm passing this disk. And then the switch flipped and I realized what the problem was. All right, now let's see if this has fixed the issue. Okay, and now we are getting something different. So we can read the boot sector, but reading the FAT seems to fail. Alright, so let's try to figure out why. And here is the... and here's probably why, because the number of sectors per FAT is 0. I think that might explain it. The thing is that... okay, let's try to do things a bit in a more simpler way. So right now the image is set to I think it's using FAT32. So let's start with FAT16 because that one is a bit easier to work with, and adapting the code to work with from FAT12 to FAT16 is easier, and then we will do FAT32 after. All right, let's give this another go. Okay, it didn't regenerate the image. Let's force it to. Actually, it's easier to just delete the image. Okay. Okay, and now we are reading the boot disk. It says that there are 100 sectors per FAT, and the problem is that there is not enough memory to read the file allocation table. Required is this, but we only have this. Okay, so for this we need to remember how we wrote this a long time ago, how we implemented this FAT stuff. And we're gonna take a quick look here. Okay, so here in FAT initialize, what we're doing is we have this G data structure, which basically contains all the information like the boot sectors, the file allocation table might be here. Okay, it's in another place, but okay, let's see what we set this to. Okay, so it's basically after this data, and then we are checking that it is underneath this memory FAT size, and here it is. So what we have here is you know, memory management is not something we have in the boot area in stage 2, and we're managing memory using this file, and we're managing it manually. So we're basically saying here that we want to use this address for all the FAT data, and we are limiting it to this number. And the reason why I'm using 10,000 hexadecimal, which is 64 kilobytes, is because of the weird real mode stuff, which, you know, a segment has the maximum size of 64 kilobytes, and if we want to read the data to this area and we go, you know, we are trying to read more than 64K, then that will fail spectacularly, because memory addressing in real mode is weird, and it's a nightmare to deal with this stuff. So it's easier to just keep things under this size and keep it aligned so that it can begin at where, you know, one of these segments begins. Okay, so what can we do to fix this? Now, this is something that we would have had to do eventually, because this the file allocation table is basically the table which describes which blocks, which clusters each file has. And yeah, on a floppy disk this is gonna be kind of small, will be pretty small. But when we're talking about, you know, 8 gigabytes or a couple of gigabytes for a disk image, then this file allocation table may actually become pretty large. And it's not gonna fit in memory, and it's not a good idea to keep the whole thing in memory. What a good idea would be is to basically cache it. So we're reading a part of it, we're not reading the whole file allocation table, we should only be reading like a part of it, and then keep that as a cache. And whenever we want to read some new data, we look at the cache. Okay, do we have this part in cache or not? And if we do, we use the cache, which will make things a bit faster. But if we don't have it in the cache, then we will have to read it. And basically, that's what we have to do here. In theory, we could expand into the memory area, which is beyond 1 megabyte, where we have plenty of space. We have a lot of space there. Yeah, we haven't done any memory detection yet. We don't know if there are any gaps that we should worry about. And this would be a thing that we would do if we had a memory manager. So, okay, we will keep things simple this time. And we will implement this caching mechanism. So instead of reading the entire file allocation table, what we will do is we will keep just a more limited part of it. Okay. This portion which reads the file allocation table used to be is part of the FAT initialize, but we don't need to do this anymore. What we can do is we can basically initialize a piece of memory. So, okay, let's start by defining the cache size. So cache size, so FAT cache size. And let's have this, I don't know, 5 sectors. Does that sound good? 5 multiplied by sector size. So this will be the size of our cache. In fact, let's just keep the 5. Let's keep it in sectors. All right, and now we don't need to do this, whatever we did here. We can just add it here, uint 8 FAT cache multiplied by the sector size. And we kind of need some additional information. We need to know where we are looking at. So, okay, let's add the position basically. And, you know, this will be the sector relative to where the file allocation table begins. So, okay, let's initialize this number. Instead of, okay, we no longer need to do this. And we no longer need to calculate the FAT size. We no longer need to read the FAT. But what we do need to do is to set this cache position. So G data. And let's initialize it to some number that is not valid. So let's say that -1 or whatever this is. Okay, it's a capital D. All right. Hello there. Okay. And now whenever we need to access something from the file allocation table, let's see where that code is. Okay, so it's here. This is the code that accesses the file allocation table. Okay, let's create an indirection for that. So I'm gonna create a uint32 fat get. Actually, this is exactly what this does. So yeah, this is exactly what this does. It's trying to calculate the index in memory at which this cluster exists. And then this works for FAT12 because there we have the 12 bytes per the 12 bits per FAT entry or whatever. Okay, so yeah, something we need here that we don't have is to detect what type of file allocation table we have. And the way we can do that, okay, I kind of started here, but I did not continue because I ran out of time last time. And there was a... Okay, so this is what we have. If the number of total clusters is smaller than this number, then we know that the file allocation type is FAT12. But for FAT16 and FAT32, I don't think this detection works very well. What we have to do instead is to look at this header, which is the file allocation size. Where is it? Oh, I can't find it. Okay, this is the directory entry, that's why I couldn't find it. There is a field here which says how big the file allocation table is. And it also mentions that, come on, where is it? Okay, here. The number of sectors per FAT. And this is only true for FAT12 and FAT16. For FAT32, this number will be 0. And we will use another field, which is here somewhere. This one. The number of sectors per FAT in FAT32. All right. So, let's add this piece of code. Now, to determine the number of total clusters, we have to do these calculations here. Okay. Now, I do already have something similar. Here in FAT initialized, I'm basically calculating the data section LBA, which is where the data section begins. And that's what seems to... Okay, and the number of data sectors is basically how big the drive is. And we don't have that information. I think we need to get that from the partition information or from the disk. Okay. And we have it right here. Okay, so we have set it in the partition size. Okay, so let's pass the partition through, and then to detect how many data sectors we have, what we need to do is go to disk and get the partition size. Now this partition size is in sectors, which is good, which is what we want. And then we need to subtract the data section LBA. So we're basically removing all the headers. And then we're dividing this by the number of okay, the boot sector is here in this BS thing. Boot sector, cluster, sectors per cluster. Okay, so this is not in sectors, this is data clusters. Okay, so we're basically calculating the number of sectors, which would be the size of the partition from which we remove the where the data section begins. So we're removing all the headers and then dividing that by the number of sectors per cluster, and we end up with the number of clusters of data. And if data cluster is smaller than 4085, which I think has some significance in hex, I'm curious if... Okay, so it's FF5, and hello, the booster, Frantic Bio. Hi. I think I prefer to use this hex number instead of the decimal because it makes more sense. Because this is 8 bits and this is 12 bits. Okay, so FF6 through FFF are kind of reserved. Okay, so if the number of data clusters is smaller than this number, then we can assume that we have FAT12. So the FAT type, I think this is the variable I was intending to use, yes. So the FAT type is 12. And else, let's look at the boot sector. As I was saying earlier, for FAT32, what we have to do is check that this number is 0. So if this number of sectors per FAT is 0, then we know that this is FAT32. Okay, so if the number is different than 0, then we know that this is FAT16, else we have FAT32. Okay. Yeah, so we need to update this readFat function, which was using the old gfat. And what we need to do here is to pass a number telling it the index. So index LBA index. Okay, and then when we read, we are not going to read. Okay, this is where it begins, to which we have to add the index. And then here, for the size, we're using that fat cache size multiplied by the sectors. Not multiplied by the sector size, because this is passed in. This is a number of sectors. Okay, and then g data fat cache. Okay, so what this function will do is it will read whatever index we give it here, starting from that index. Okay, so now let's go to this next cluster function. And here we have three cases, depending on whether we are using FAT12, FAT16, or FAT32. Okay, so let's calculate the index. If the FAT type is 12, then the FAT index. Okay, so what this means is basically the index, okay. This is essentially the binary index, so the byte itself. But which byte we need to read? This is what this index is means. If the FAT type is 16, sorry, then the FAT index is the current cluster. Okay, so in FAT16, each cluster has basically 2 bytes. So it is the current cluster multiplied by 2. And if the FAT type is 32, then the FAT index is the current cluster multiplied by 4. All right. Okay, so determine which entry we need to read. Determine the byte offset of the entry we need to read. That's the first step. Okay, then we need to convert this index into a number, into a sector. Make sure cache has the right number. Okay, so FAT index sector is the FAT index divided by the sector size. Okay, and how do we find out if this is in the right range? So if FAT index sector. Okay, what we need to do here is to determine if this is not in the right range. So if the FAT index sector is smaller than the FAT cache position, that's where the cache starts. Or if the FAT index sectors is greater or equal to the FAT cache position plus the cache size, then it means that we have a cache miss and we have to read that portion from the disk. So we will do read FAT of the partition. Okay, so we don't have the disks here, so we need to pass it. And then the index, we'll just use this FAT index sector. All right, So now we have determined that, okay, if this is a cache miss, we need to read that from the disk and then store that in the cache. Okay, now we need to determine, okay, so we know that the index in the entire file allocation table, but we don't have the entire file allocation table read here. So what we need to do is basically subtract this fat cache position multiplied by the sector size. So fat index minus equals the fat cache position multiplied by the sector size. And that should give us the position in our cache that we have read. Okay, and then yeah, we need to have again separate cases for FAT12, 16 and 32. Okay, and for FAT12 we have this odd and even thing. Then for FAT16, all we have to do is just return this number. We don't have to do any kind of special handling. And for FAT32, it's almost the same, but this time it's a uint32, and that's basically it. Okay, now, yeah, I think we can comment this. If we want to add exFAT support, then yeah, we might want to keep this, but the else is fine. Otherwise. Alright, so this should solve the problem that we had, that the file allocation table doesn't fit into memory. Let's see if we have any other errors. Okay, so here when we calculate the next cluster, we also need to pass in that disk thing, so... okay. Okay, so... let's give this a try and see if it works with FAT16. I think it should work with FAT16, but I'm not sure if I didn't get anything else wrong. Okay, kernel.bin not found. And I know why. Because kernel.bin is not in the root directory, it's in the boot directory. Okay, let's see if this works. Okay, fingers crossed. Hoping it works. Okay, it did not work. Okay, so maybe we have some other things, some other assumptions, some other places where we need to update this code to work for. Okay. This sounds like a bit of a shot in the dark, but let's try to find 12. Maybe there's something hard-coded around here. Okay, no there isn't. Okay, it was worth a shot. Okay, but let's see what we got so far. So... boot not found, but that is a funny character there, and I don't think it should be there. And maybe it has to do with some parsing or something. Let's figure that out. Okay, so what we are doing here is we are going through So this is exactly what we're doing here. We are trying to basically find where the next slash is, and then extracting that, and then converting it to upper, I think. Because that's how... I am not converting it to upper anywhere. Okay, that might actually be the issue. But wait, the kernel.bin wasn't in uppercase, so it has to do that somewhere. Oh, okay, so it's this fat find file. Okay, which basically does the conversion to upper. Yes, okay. That makes sense. Alright, so yeah, something is not really working correctly, and I'm not really sure what. So let's try to figure this out. Alright, so let's go to FAT open first. And the way we're gonna debug this is through the everyone's favorite way, using printf. I think that's the easiest way, because this C code, it's kind of hard to debug using GDB without having symbols. And yeah, that's another thing. If we want to do symbols, the best way to do that is to basically use elf instead of binary. So to do that, what we would need to do would be to output this in elf format, and then implement a very basic elf reader inside stage 1, which is a bit challenging, but it's not that difficult. But this advantage, I think, is very good, because then you would have symbols. You could use symbols with GDB. You could tell GDB, okay, here are the symbols, and then you have normal debugger experience. You don't need to go through assembly code anymore, and that would be great. Anyway, yeah, let's try to figure out what is happening here. So, okay, the first thing we are trying to do here is to basically split the path into parts. Okay, let's see if this is working correctly. Okay, let's print this name variable. Okay, and yeah, it does look like it has a character it shouldn't have. So there's definitely a bug here. I'm not really sure where, but let's try to figure it out. Yes, exactly, Duffelpole. I agree with you. Why the hell is it doing that? Alright, so maybe it's one of these... This sounds like this is one of the most common problems in programming. +1 errors. Off by 1 errors. Yeah, that's a very common problem in... I think it might be this thing. Because what we're doing here is... Okay, so let's think about this logically, what this code is doing. We are trying to find the slash character, yes. And then if we do find a slash character, so if it is not null, then we copy into the name variable, starting from path, which would be the beginning. And the length is this minus the path. Okay, so Let me get my notepad here. All right, so if we have... Oh, no longer need any of this, so it goes. Okay, so let's say that we have this string boot slash image dot, I don't know, kernel dot bin or whatever it was. Okay, so the first instruction is if path of 0 is 1, then we advance path. So now path looks like this, right? Because we advanced by 1 character. And then here we are searching for the delimiter, so we are getting the position of this slash. So that would be here. So this is where the lim is. Okay, so in our case that would be 0, 1, 2, 3, 4. So the lim equals 4, and let's say that path equals 0. It doesn't matter what the actual address is, just the offset from the path. Okay, and then we are copying from name to path by 4 characters. So we are copying 0, 1, 2, 3, 4 characters. Okay, that should be correct. And then we are setting in delim minus path, which is 4, plus 1. We are setting the null character. Yeah, this is the problem. So, because we are setting the null character to... Okay, so we have copied this boot to some other place, to this name variable. And then we're setting... Okay, so this is 0, 1, 2, 3, right? And we were setting the lim minus path. So we were setting, this is 4 plus 1. So we were not setting this character here to null. We were setting this one, the one after. So that's the problem. Off by 1 error. All right, and then after we have done this, we need to set the path to delim plus 1, which means we're setting the path to this one, which makes sense, yes. And then we have kernel.bin. So there you go. I think this might be okay because it worked so far, so... Okay, let's give this a try and see if the issue is fixed. Okay, something happened. We don't know what, but something happened. So what I think might be happening is that we have read something, but probably the wrong thing. So we did find the file, which is great. That's the first step. Finding the file is the first important step. Right? And we did find the directory entry. Okay. Okay, let's print some information here and see what we got. Alright, so when we do this file open, let's see, file, position, size. Okay, there's not much to go on there. Okay, actually let's go into FAT read and try to figure out what this function is doing, because I think this might be more useful. Alright, we have some checks here and... Okay, let's print this partition read sectors, because I think this might actually be more useful. We can even go as far as using this disk read sectors. Fine, partition read sectors is fine. So let's print what it's trying to do. We already know it starts from 2048, so that doesn't matter. LBA sectors. Okay. Oh, and I think I know what the problem is. I already... Okay, so you know what the problem is? When we are reading the next cluster here, what we're doing is this. We are checking it against FF8, but the problem is FF8 is only valid for FAT12. So let's convert that to something else. Okay, so for FAT16 that is 3 Fs followed by 8, and for FAT32 it's a lot of Fs followed by 8. Okay, so what we could do here is inside this next cluster function, okay, instead of returning, let's do... Okay, so let's create a variable here. Okay, and we're gonna set the next cluster to this. Okay, and if the next cluster is smaller or equal to FF8, then we will just add the rest of the Fs here. So next cluster, let's add the other Fs. So that would be FFFF, FFFF, but without these three. All right. And finally, return next cluster. If the next cluster is larger than F8, then we do the same thing. So next cluster, we add the upper half of the Fs, because we already have like a couple of Fs here, so we only need to add the missing ones. If I write this like 0, 0, 0, 0, then, you know, this makes sense, right? Alright, and for FAT32, we don't need to do anything. Alright, let's give this a go and see what happens. Oh, and yeah, I forgot to update the code where I check for this stuff. So it's not FF8 anymore, it's a lot of Fs. It's 1, 2, 3, 4, 5, 6, 7 Fs and then 8. It may not be this problem, maybe something else, but it's a good candidate. Okay, so we are reading something, but it still doesn't look right for some reason. And we need to figure out why. So my guess is that maybe I'm doing something wrong in this caching code here. It could be, I don't know exactly. Okay, so let me just take another look at the code to make sure that I haven't made any mistakes. So the initial at cache position is FFFF, a lot of Fs. And this condition will be true, no matter... This condition will definitely be true. Which I think is fine. Okay, and then it's reading the file allocation table. Okay, you know what we need here? I made a video about it. The last video. It's scrolling too much, too far up. Let's get that E5 debugging here, because I think that might be very useful here. Yeah, so I'm just gonna do the simplest thing there was to add this, which would be to edit here input C, output E9 and a character. I just want to see all the logs without it going beyond the screen. And then in over here, let's add that argument. So std debug con stdio. Let's see if this works. It should work. Yay! So now we can scroll up, which is great. Okay, so this is weird. It looks like the first sector that we are reading is sector 2208. Okay, which probably makes sense because we start by searching through the file, through, you know, that directory entry table, right? So I think this makes sense. And then, okay, so this is a cache. This is, we'll try to read it from LBA8, which is where the stuff is. Okay, so that would be starting at 800 is where... okay, so it's not 800, it's 800 multiplied by, where's my calculator? I've lost it here. Okay, so let's go to where that partition starts. That's where what I'm trying to find here, which would be at 800 multiplied by 512. And let's convert that to hex. So this is where we need to go. Can we tell... Okay, go to... Yes. Okay, so this is where the file allocation table... This is where the actual partition starts. And... okay, this would be the boot sector. Then... Okay, we have some empty space. And then we have the file allocation table. It's right here. Okay, so in theory, this should not be necessary. This should only be... It should only need to read this once. And what I'm seeing here... Oh, I know what I did wrong. I know what I did wrong. Here, when I read this, when I fill this cache, something that I forgot to do is to update the cache position. So it's reading from the cache multiple times. You can see it's reading here, even though in theory it should already have that data from LBA8. So that was the problem. All right, is the FAT index sector. Okay, so we have read from the cache, so we need to update this. Okay, let's see what happens if we run this now. Okay, this is different. But for some reason it's still not working. Which is odd. Why is it doing that? Why? It's not sconce which is slow, it's the guest mount actually. It's the guest mount is slow. If we didn't have to use guest mount, it would be a little faster. It's not sconce. And of course you can use sconce with multiple threads. I think it's -J. I'm not sure, but I think it's -J and then the number of threads. So you can use sconce to do stuff in parallel. And in theory it should work. Okay, so this is where we are reading the file allocation table. Okay, let's also print whatever we're getting here, because something is odd and can't really figure out what. In this conversion code that I wrote, where is it? Okay, here it is. So let's print the stuff. Let's print a lot of information. Let's do printf. So fat, what was this? Fat index. Let's print everything to the screen because I need debugging information. I need to know what is happening to make sure that all of these calculations are good. Let's also check that the detection works properly. I don't want to see this to be 12 or something like that. Okay, what else can we print? We can print... okay, the next cluster, yes. Okay, so... What? Why is the fat type 0? Oh, I know why it's 0. Oh my god. The things you forget, sometimes. I forgot to call fat detect, so right after initializing everything, let's call fat detect of disk. Okay, this looked... Hello from kernel! Yes, it works! Yes, yes, yes! So, we are reading from FAT16 and it works. That's awesome. Now it's time to do FAT32, and let's get that working. Okay, so for FAT32, what we need to do is to basically change a couple of things. So, in FAT32, we have these extra headers in the boot sector. And, yeah, we need to basically take care of them. I'm not even sure if I even have them here. No, I don't. Okay, and I may not even have them in stage 1. I'm not sure if I have them in stage 1. But this doesn't matter because we're not really using the file allocation table here, so we don't care. Stage 1 should be fine. Actually, the only thing I'm concerned about is that it might overwrite some data. And we need to make sure that doesn't happen. So... Okay, we did last time, we created this conscript file, and here I am declaring this define, which contains the file system, and I haven't used it, so let's use it. so yeah, for the file system headers, first we need to create some defines here. So define FAT12, FAT16, FAT32, and it was X2. These are the ones that I decided to support. I'm not sure if this is gonna work. Okay, we'll see in just a moment. I think I might have to do something like this. Okay, and then here what we can do is, so if def or if file system is FAT12 or the file system is FAT16 or the file system is FAT32 and if. Okay, let's see if this looks good. Okay, yeah, looks like Nazem is happy with my code. Okay, let's clean this up a little bit here so it's a little cleaner. All right, and now let's see what headers we need. Okay, so for up till this large sector count, large sector count here. Okay, so up till this point, this is common for all the file systems. But this section here, it only applies to FAT12 and FAT16. For FAT32, we have other flags. So let's add those instead. If file system is one of these two, then we do this. Else, if the file system is FAT32, then we will use these. Okay, and okay. No, what are you doing? I want to put a cursor in front of everything and just comment everything at once, so. Okay, so first we have the sectors per FAT, so let's just call this header FAT32 sectors per FAT, which is 4 bytes, so DD, and just giving it a number, doesn't really matter what. Then some flags, word, FAT version number, which is also a double word, double word. All right, the sector number of the FS infrastructure, so FAT32 FS info. And the backup boot sector. Then we have times 12 dp0, so we have a couple of reserved bytes. Then the drive number. which is a byte. Int flex is another byte. Then the signature, which is byte. Serial. So basically the disk serial number, which is a double word. And then the volume label, which is times 11 dp0, 11 bytes, and then the system identifier string, so FAT32 system, then the fire string. Okay, we don't really care about what the data is, we just care about having it here so that nothing is overwritten when we install stage 1. Okay, let's see if this... Have I used the EBR stuff anywhere? So I've used the drive number in some place. And it's here as well, so... Okay, so this is... Okay, so it looks like we might be able to reuse... To me, everything below this drive number looks identical from here and here. So db0, then these flags which I just didn't declare here, the signature, the volume ID, and then the volume label and the system ID. Yes, so what this means is that all we have to do is just put this above this EBR extended boot record structure, and then we can just leave this for all the drives, and I think this should be fine for all the file systems I meant. Okay, which I think looks good to me. And now we can use the drive number and whatever I used here, just reusing this data without any issues. Okay, this looks good. Now let's go into stage 2 and see what we have to change here. So again, we have to update this structure to have all the FAT32 stuff. Let me think about how to do this. So this is essentially the boot sector for all the drives. I would love to reuse this. Okay, so what we're gonna do is just a union. And let's move these out to a structure called EBR, extended boot record. And then what we have to do here is have a union, and for FAT12 and 16 we are using this entry, which contains this extended boot record. Actually, no. Let's create a structure and call this FAT1216, and then we'll have another structure which is called FAT32. And what we have here is just the EBR. And here we have the EBR with some extra stuff. And we definitely need to use the attribute act here to make sure that there's no padding added to any of this stuff. Okay, does this stuff have a name? No, it's just called... Okay, so it's just the extended boot record for FAT32. Okay, so I think I can just... Okay, so let's just use this one instead. And I'm gonna call this EBR1216. And I'm going to create another structure. And this will be the FAT32 extended boot record, which will contain the FAT extended boot record. And then all the other stuff, the extra stuff. And let's copy that from stage 1. Alright, so this is U in 32 sectors per FAT. Alright, so this is it. This is the FAT32 extended boot record. And we'll call this EBR32. Okay, I think that's... I forgot to replace elif with if in boot.asm. Really? Oh, yes, thank you. Thank you. Good catch. Thank you. Someone is paying attention. I'm very happy to hear that. Right. Okay, so what's next? Let's see what's next. There's also this file infrastructure, which is usually stored in one of the reserved sectors. This is why FAT32 has at least minimum of 2 reserved sectors. Okay, I don't see a layout here, but basically that's what this is for. So this FS infrastructure. And let's see what this one has. It has some signature, some reserved bytes. Okay, so it looks like these bytes might be used for the boot the continuation of the boot sector, because it's 480 bytes. Okay, and then we have the last known free cluster count on the volume. Okay, so this is interesting. This is probably... Okay, so this is probably used to determine how much disk space is used. It's nice that the file system has a structure for that. It has a field for that. And then this number indicates the cluster number at which the file system driver should start looking for available clusters. Okay, so this is just optimization so that whenever the operating system needs to write something to the disk, it can quickly find that information a lot faster than it would have to if it didn't exist. And then reserved, and then some trail signature. Okay, so this doesn't have any interesting information for us in this implementation, but yeah, for a full operating system where you are doing writes, yes. We do need to add FAT32 to the kernel, but the problem is we don't have the VFS, we don't have a memory manager, and we don't have any kind of disk driver. Because in stage 2 we're using the BIOS, and this is not something that we can do in the kernel. This is fine for the stage 2 bootloader, because yeah, we're still using the BIOS as a crutch, but once we're in the kernel, it's a very, very bad idea to do that. If you've ever used old versions of Windows, like Windows probably before even Windows 3.1. So Windows 3.1, Windows 3.0, they still used the BIOS functions for reading from disks, and it was very unstable because of that. In Windows 3.1, I think they changed that. Yes, we need to wait, unfortunately. There's no other way. We do need a memory manager for this, because I mean, this is a very crude way of memory management. Don't get me wrong. Yeah, if you have, like, I don't know, you're doing embedded development and you are writing code for an embedded device, and you know exactly how much memory you need to use. And you also need that device to be very stable. You know, you can't afford to have... this is basically for real-time applications. Then this is fine. This is used in real life, this stuff like this. Yeah, but unfortunately, it's not good enough for us, because we're not creating a real-time kernel here. We are creating a normal kernel. There are real-time kernels, like I think there's a version of Linux, but it's not actual real-time. It's more like it has some optimizations and some changes to make it behave more like a real-time operating system would. But I think there's VxWorks, if I remember correctly. VxWorks, yes. VxWorks is deterministic, so this is kind of the main point of this operating system, because you don't allocate memory, and you try to avoid doing anything that has a variable amount of time that it could take. So this is the whole idea of real-time operating systems. They need to be very, very predictable, because they are used to control, I don't know, lasers that burn your eye and that kind of stuff. So for that application, that's what these real-time operating systems are for. And yeah, it's kind of difficult to make, and there's a lot of work that has gone even in VxWorks, in FreeRTOS, and other real-time operating systems. But yeah, there are applications when even if you miss, you know, if you move the laser or if you turn off the laser a few milliseconds later, that might make the difference between a very angry patient because his eyes aren't working anymore, and he's gonna sue you, and you don't want that. So yeah, that's something very interesting that I learned a long time ago about these. Yeah. Thank you for the encouragement, Andrei. Happy to share my knowledge, basically. Okay, so let's see, where are we at? Okay, so we have added this extra information here. Now we have this detection code. where we are detecting which file system we are using. Okay, now if the file system that we have detected is not okay, so now what we need to do is, for example, here we have these sector, where was it? Sectors per FAT. So we know that this is 0. And for FAT32, we know that it's not 0. It's actually in another structure. It's inside this EBR32. It's right here. Sectors per FAT. It's a 32-bit number. It's not a 16-bit number anymore. So this is kind of what we need to do now, is to make it so that after we detect the file system, we use the right values for each of these parameters. Okay, so now that we know that in the boot sector this is no longer valid, this sectors per FAT, in that case we need to create a separate value. So let's declare here a static variable, g sectors per FAT, and we are going to set this. Okay, so we did the FAT detection. So if g FAT type is 12 or 16, then the sectors per FAT will be the one from the boot sector. So gdata.bs.bootsector.sectors per FAT. And here's a little problem, I think. Here we are calculating. Okay, we're just printing stuff, so I can delete that. I need to make sure that we're not using this before we set the value. Okay, we're using it to calculate. Okay, root directory LBA. Okay, so we're using it to calculate where the root directory is, which is not ideal. Okay, so in that case, we need this number even earlier, even before we actually do the detection. Okay, so could we do the detection earlier? We need this data section LBA here, which is probably the problem. Which is why we can't do the FAT detection earlier, because we need this number and we don't have it yet. Okay, so in that case, let's calculate this. Let's do sectors per FAT. Where are you? So it's being used. Where is it being used? It's being used here to calculate, to find the root directory file position. Okay, so in that case, this is where we need to read it. And what we can do is take this value, and if it is 0, then we will use the other one. So if g sectors per FAT is 0, then we know FAT32, and we will read the other value from sectors per FAT equals g data boot sector EBR32 and sectors per FAT per FAT not flat. Okay, and instead of using this, now we use this new variable. So let's see if we use this anywhere else in the file, because we need to replace all the usages. This is no longer needed. Okay, and this is in the FAT detection code. So this is the only place where it's actually used. so it is fine. All right, and let's see what else is different, because it's not the only thing. So in FAT32, the number of, okay, we already looked at this. Then we have the cluster number of the root directory. Often this field is set to 2. Alright, we probably should go to this code section at the bottom and look at the examples and see what is different. So, total sectors in volume. Oh, so there's a total sectors. What is that? Where is that coming from? Total sectors 16? What is that? Is it the size of the disk? Oh, yeah, so it looks like it is. Hold on a second. Okay. So it looks like we do have a total number of sectors of the disk. But I mean, it's better to use the... Okay, let's take these numbers and see them. Are we using this anywhere? I don't think so. Okay, we are using it to determine the number of data sectors. Okay, now this might be a good idea to do this because, for example, if you extend the partition, then the file system will not know that the partition has been extended, and I think it might be better to use. Yes, it might be better to use this instead of the partition size when calculating the number of data sectors. Okay, we will change that. Okay, so essentially what we have here is a couple of other interesting information. Okay. Okay, so let's add this as well. Static uint32 total sectors. And let's do the same here. So total sectors equals sector total sectors there. No. How is it called in my code? Total sectors, yes. I thought it was called something else, but it's not. Total sectors. And if this is 0, then we know it is FAT32, and we will act accordingly. And where is that stored? It actually might... Okay, so it's not in the extended region. It's right there, after the hidden sector count. Interesting. Total large sector count, yes. And... Okay, so if the number of total sectors is 0, then we have to use this large sector count. Okay, that makes sense. All right, let's see what else we need to... Okay, we've already determined the size of the table. Then the number of root directory sectors is the root entry count multiplied by 32. Okay, so this one looks like it's still valid for FAT32. Oh no, unless you have FAT32, in which case the size will be 0. Okay, that's another interesting thing. So we basically need to use the information we got here, that it's FAT32. So if the number of sectors per FAT, then okay, let's say boolean is FAT32. I don't like it. Otherwise it's false. This is a bit messy, but yeah, okay, so the size of the root directory for FAT12 and 16 is same as we had it before, so basically this. Okay, so if is FAT32, then we will have the root directory size equal to this calculation. So the okay, so it is the root entry count multiplied by 32. Where did I use this? Okay, here, root directory sectors, where I'm just rounding. Okay, that'll make sense. Now, we know that for FAT32, it has a root directory, what? Let's see. Okay, so for FAT32 we consider this number 0. And in FAT32 the root directory is no longer part of the header. I think that's what this article is trying to say here. Because in FAT32 this will be 0. So essentially in FAT32 the root directory will be part of the data section of the disk. It's not going to be part of the header like we had in, and we do have some headers which tell us where the root directory is inside this extended boot sector, boot record. Root directory cluster, here it is. Okay, so if let's set this to 0, and if it is not FAT32, then the root directory size is this. If it, and also the LBA, I think this should also go here. Because for FAT32, okay, so let's just not have a double negative here and put this in the else. So if we are using FAT32, then we know that the root directory LBA is going to be in G data, yes, boot sector EB R32 dot root directory cluster. And here's the tricky part, because this is a cluster number, so damn it, we need to calculate it differently. I think we might need to calculate it a bit later. To convert from LBA to from a cluster number. Okay, I'll have to go over that a bit later. So let's put a to-do here. Okay, so we are calculating the root directory LBA and the root directory size. And then we are trying to initialize basically this file structure, which contains all the information about this root directory. And we are trying to read it into memory. Okay, this would be the root directory size in sectors, which would be the root directory size. If it's 0, then this will also be 0, which is fine. Okay, this looks good so far. Okay, so what I think we should change here is how we do this calculation. Because basically we're trying to obtain this data section where it to understand where it begins. So in this case, the data section begins here. And the root directory sectors, let's also put it in here. Okay, so the data section is at wherever the root directory begins, plus the size of the root directory. But in FAT32, the root directory is not part of the header anymore. So the data section actually begins at after the file allocation tables. Okay, we'll figure this out, this root.dir LBA later, but the data section LBA is at the number of reserved sectors plus the number of sectors per FAT, which again is now this global variable, multiplied by the number of FAT, by the FAT count. Okay, and let's not forget that to do this a bit later to fix this. Okay. This is no longer necessary. Okay, now for cluster to LBA, we are using the number of sectors per cluster. Okay, I think this might be okay. Now that we have calculated where the data section begins, we can use FAT cluster to LBA to make the conversion. And of course the size is 0, so... Okay, that looks pretty good to me. Let's see what else we need to change. Okay, we have already calculated where the first data sector is. This is exactly what we did right now. And I don't really see any other change. Okay, so I think we are good. I'm not 100% certain, but I think we might be good. Let me check a few things. Okay, so this detection is basically... Okay, yes, so here we calculated this number of data clusters, and as I was saying, instead of using the partition size, we should be using the total sectors count. So this is the size that the file system knows that the disk is. Okay. I am not certain if this is gonna work, but let's give this a try. Let's see if we broke anything first, and then we will try. Okay, there are some errors. Oh, so cluster to LBA is not declared. Let's just declare it here at the beginning to make sure that I've replaced them everywhere. Okay, I'm only using this for the detection. And this one should be good. I think we might be fine. Ah, okay, moment of truth. Let's see if FAT16 still works. I am not 100% sure, but okay, it works. Great, great, great. So FAT16 still works. So let's check. Let's try to do FAT32. Okay, anyone want to guess? Will this work or will it not work? From my experience, I'd say that this will not work, but does anyone want to guess what's gonna happen? Moment of truth. Oh my god. Okay, so it did not work. Okay, so the problem seems to be that in the boot sector we need to compress things because there's some overlapping going on, which means that our boot code is too long. Ah, damn it, FAT32 with your extra bytes here. I don't even know what to delete from here. I know, I think I might reduce the size of these, Yes, this sounds like a good idea. So read from disk. Who needs that many useless words? File not found. Who needs that many? So many useless and wasted words. Wasted bytes. I need those bytes. Okay, how are we doing? So... okay, we have reduced the size a bit, but we're still getting some overlap. I think 6 bytes is how many we need. I'm not sure, but I think... we don't need the loading message. Can we delete the loading message? Yes, I think we can delete loading message. Who needs loading? Wasted code and bytes, right? Okay. Yes, that seems to work. Now, I have no idea if this is gonna work. I'm not... oh my god. This is amazing. I did not expect this to work on the first try. I really did not. But yay! This worked on the first try. So we have support for FAT12, FAT16, and FAT32. Okay, before let's try this with a floppy disk as well. Let's make sure we haven't broken anything, because that is still a possibility. Okay, I think I will need to sconce clean and then to force it to regenerate the image, and it seems to work. And fat type is 12. Yay! Okay, so this works. Okay, and if we switch back to disk, then yeah, of course this works because we just tested it. Here we go, fat type is 32 and we are in the kernel. Oh yeah, that is great, that is awesome. That is awesome, I love it. Let's commit the code then. And I think, okay, this looks good. These changes in the box configuration, sure. I'm not sure about this one. Maybe, whatever. You can change it. You can change stuff. All right. Alright, then the changes in the bootloader, where we are compressing it and removing unnecessary code to make it fit. Okay. Then these comments. I'm looking for the printfs. I want to delete the printfs, which are not necessary anymore. Okay. Okay, this is one of them. And the other one, I think, was in that disk method. Okay, this one is no longer. Yes. And I think we can leave that. It's not gonna do anything bad. Okay, so we have FAT16 and FAT32 support. And I think we could integrate this into the main branch, into the master branch, because the whole reason why I created this separate branch is because because these were breaking changes and I did not want the main repository to be broken. So okay, let's see how we can merge. How the hell do you merge in this thing? Because I've never used it for that. Merge branch to master. Oh no, there are merge conflicts. Okay, but it's just these two files. And I just added debug_con. And here, yeah, debug_con stdio. So we can just leave them deleted. So accept all. No, okay, this is not going the way I want it. It should not merge master into bootloader 2.0. It should be the reverse. So how can I abort this merge? Oh, how does this even work? It's not like I use Git at work. Yeah, I know how to fix the conflict. I'm just trying to figure out how to drop all the changes, basically. And okay, let's just use smart git because it's smart. I think Git is a bit overly complicated at certain things. It's great, but I admit it's a bit complicated for certain things. Just adding the repository. All right. And we can abort the merge. And now we can go into master. And branch, merge. What are these? Okay, branches. We want these. Create merge commit. Okay, and we have these. So we will accept the incoming, basically. Take the... Why? Okay. Can I just delete these? So discard. Yes. I don't know what this will do, but we will see. Alright. And let's commit. And now let's see what we've broken, because I'm pretty sure, okay, these files should be deleted. That would be one issue. Seems fine so far. Okay, it works. We have a successful merge here. Alright, so these are the messages that I had in that video. Okay, perfect. Okay, then I'm going to commit removed run files. Yes, and let's synchronize all the changes. Okay, where's okay, I think this looks perfect. Yes, perfect. Okay. Yeah, should we do something else? I was thinking about maybe trying to do the VFS, or no, not the VFS, the V, what is it called? The long file names basically, the VFAT, yeah, VFAT. Should we do the VFAT as well, so we can support long file names? What do you think? VFAT, yay, VFAT for everyone. All right, so VFAT is very ugly. The way it works is, let me see if I can find an example here, because it might be easier to show. Okay, scroll. Okay, might be a good idea to reload this file. Ah, damn it. Layout. Default. Okay. So address 10,000 something was where this began. So, okay, where is the root directory? Good question. It's in here somewhere. Okay, let's see in those headers. The nice thing about these headers here on OS Dev is that it gives us the offset, so it's easier to find. Okay, so for FAT32, the root directory cluster is typically 4, but whatever, so it is at offset 60. 60 is here. Maybe this is not correct. Is it 60, right? And it is 4 bytes, and it's typically 4. This looks weird. Okay, why does it say FAT16 here? Anyway, I'm a bit confused. So, in theory, this should be a FAT32, but what's up with this? Why does it say FAT16 here? Okay, so let's check some of the numbers that we expect to be large. So... oh, there's a problem. I was looking at the exFAT boot record instead of the FAT32. Oh man. So we are looking. Okay, so at offset 24 should be the number of sectors per FAT, which in our case 24 is here. Did it say 24? And... okay, this is still strange. I don't trust this. Let's try to reload. Maybe something wrong about this tool. How do I reload? Okay, I just... Okay, so go to... it was a big number. Okay, this one. Okay, so it's still saying FAT16, which is strange. Okay, let me just bring this up. So there, I don't have to switch between screens so much. Okay, so the number of sectors per FAT is at offset 16. So this one should be on 6. This one should be 0, but it's not. Is this a FAT? What is going on here? It says that we are formatting using FAT32. Seriously, what the hell is going on? Okay. All right, let's check. Config.py. So it should be fat. Oh, the image size. Okay, it should be fine. I mean, the default is also 250 megs. But it should be fine. Something is weird. And I cannot... And I'm not sure what. So... Maybe... I don't know. Am I looking at the wrong file? No, it should be this image.img. I think I might be looking at the wrong file. Hold on a second. Hold on a second. Hold on a second. Open file. We are here in build. Here we go. Here we go. Yes, it is FAT32. Oh, okay. I was looking at the wrong file. So this file is from another path, from another folder where I do this stuff. Yeah, okay. I'm sorry about that. Okay, so what I wanted to look at was this. Okay, the cluster number of the root directory, which would be at 2c. So let's go at offset 2c is over here. Okay, so it is at cluster number 2. And to convert from cluster to an actual sector, it's basically, we need to figure out where the data region is and then subtract, I think, 2. Whatever, let's just... Okay, these look like the directory entries. The way they look, I think these are the directory entries. Or no? Okay, I think no, wait. This is still part of the code. So this is still part of the boot code. All the way till here, this 55AA. And okay, this is that FAT32 signature that I was talking about. And then we have the file allocation table, probably. And okay, let's scroll down until we see something. Yeah, I'm using mkfs FAT. So the problem is I was looking at the wrong directory. It was I had the wrong image file opened in imhex because it wasn't, you know, when I do these videos, I tend to create a lot of folders. For everything I try, I create a different folder, basically a different folder with all the source code. And I kind of got confused between this one and this one. That was the issue. It wasn't the tool or anything like that. Okay. Okay, so what I think might be easiest is to find the string for boot, for example. Okay, it's not like this, it's with capital letters. And here we go. So this is probably the... Yes, these are the directory entries. Okay, and let's take a look at the directory entries here. Directory entries, okay. So the first one, this NBOS, is probably just the disk label, because there is a special attribute here that you can use for the volume ID, this one. So it probably has this 8 set here so it's right after the name here. There we go. So it has the volume label. And then we have this one, which would be the boot entry. And this looks like a VFAT entry. So if we go here to VFAT, where is it? Long file names. Okay. So at offset 0 we have 1 byte which gives it the order. Okay, and then the first 5 characters. So we have BOOT. Okay, that's less than 5, but okay, and okay, so that's just an order so that we can sort all of these entries. Okay, then at offset 11 we have this. So 20 plus 11 would be what? 31. So this one maybe. The attribute, which is always 0f. Okay, it's probably this one then. Yeah, it's this one. Yeah, because these are in not in hexadecimal, these are in decimal. Okay, so that makes sense. Then the long entry type, which is 0, this one. Then the next 6 characters, and then some other number which is always 0, and then some other characters. And I think what we have here is FF put wherever the string ends. So the string ends with this 0, 0, and then the rest is filled with Fs. Now, something really ugly here is that these file entries, they are in UTF-16, so they are in Unicode 16. And unfortunately, we need to convert them to UTF-8 to be able to use them. Otherwise, we have to use wchar instead of char. And that's not very convenient. It would be best to try to convert them So UTF-16 to UTF-8 conversion algorithm. And it's an ugly algorithm, don't get me wrong, it is ugly. But basically, so I've done this before in some projects. So the way this works is that in all of these encodings, UTF-8, UTF-16, UTF-32, you basically have a representation of the characters. And using each of these representations, okay, so for example in UTF-8, you can have 1 byte characters, but then there are some control bytes which tell you that, okay, this is not just a single byte character, this one has multiple bytes. And then in the end, you kind of convert all of those to a code point. So the code point is essentially the Unicode standard. So I don't know, if we look at Unicode code points. Browse. Okay, so each character has a code point, and there are a lot of characters. This Unicode extension, this Unicode stuff is huge. And yeah, in UTF-8, you cannot fit all the characters in a single byte, obviously. So you have certain control words which tell you that, okay, this next byte is also part of the character, or these next couple of bytes will be part of the character. And then you kind of decode and get it into this code point. And a code point is, I think it's a 32-bit number, if I remember correctly. So Unicode code point. Alright, so the total size of this Unicode space is 17. So there are basically 17 planes. And each plane has 65,000 characters. And there's a total of 1 million and something. So a 32-bit number will usually be enough to represent any code point. In UTF-16, it's kind of similar to how it works in UTF-8, but there are fewer characters that have these special bytes, basically, which tell you that, okay, for this character you need to use multiple symbols. So, if we look at this UTF-16, here on Wikipedia we will find methods on how to convert this. Okay. It's probably easier to just use something that's already done for this, because at least for me this is not fun. This is not fun. Trying to decode UTF-16 is not fun. Maybe some people find this stuff fun, but for me it's not. Okay, so let's try UTF-16 to code point. Okay, so this one is not that hard. Yeah, surrogate pairs, that's how they are called. So these special characters are called surrogate pairs. Now I remember. So essentially, if we look at this code, this is what it's gonna do at first. Yeah, get Unicode char as UTF-16. So if the code is within a certain range, then we just return the code. Otherwise, we need to do some more math and stuff to obtain the actual code. Okay, this is actually doing it in reverse. Okay, so this will be the first step. Trying to implement this. Okay, so I don't know, let's put it in string. I think this is fine. So int get okay. What the hell? Okay, get, okay, UTF-16 to code point. And here let's just take a, should we use a white char like W char T? I think it might be better to just use it to have the string itself. Okay, let's just use the white char. The white char is usually 2 bytes, but nothing is... No, it's not. It might actually be 4 bytes. Oh, I hate this thing in C. Nothing is like you know it is. Size of W char T. Ah, it's weird. Okay, let's use white char in that case. I think this might be okay. Okay, so string. Okay, and here we kind of have to modify the string. So depending on what character we read, we might have to advance maybe 1 position or maybe 2 positions. So let's do... Okay, let's just have a double pointer, because these are always fun, right? Double pointers, always fun. The funnest fun you can have. Alright, and just gonna copy this little piece of code here. Yeah, it's probably gonna be safest to just use this in 16T, because we know 100% that it's gonna be 2 bytes. But white char, yeah, fine, let's just use white char, whatever. Okay, so the first character will be at string of 0, but string is a pointer, so we are using... Okay, so we are advancing this string. I really don't like what I'm doing here. So what I'm gonna do is going to... Okay, let me think about this. Okay, so what I want to do is increment string, but like this. String plus plus. But I don't like this. Okay, so let's do this differently. So let's have the return in... as a parameter, and I'm gonna return from the function, I'm just gonna return a W char pointer to the updated pointer. I think this is a little nicer. I really don't like using double pointers. Okay, so here what we can do is just string, and then we do string plus plus. All right. Okay, let's make this. As clear as it can be. So this would be the first character, and if C1 is larger than D800 and smaller than DC00. It means that this is a surrogate pair. And we have a second character, which would be the next character in the string. And then we advance the string. And we use this stuff to convert it from this to a code point. And now we have to do the reverse. We have to convert a code point to... Great. Please do the pull request for Alpine packages, please. Okay, and let's call this code point to UTF-8. What did I do? And we are going to pass the code point here. And then we need a char string output. And we are going to write to that char, okay? And let's find code point to UTF-8. Convert code point to UTF-8. No. I want the code to do that. Okay, so the following byte sequences are used to represent a character. So if the code point is between this and this, then it looks like, okay. This is helpful. So let's put this here. Because this, I think this is very useful information. Okay, so there are basically 4 cases. There are 5 and 6 byte forms, but these are obsolete and usually not used. So let's start with this range. So if the code point is smaller than 7f, then all we have to do is just write it to string output char code point. Okay, then if we are between 80 and 7ff, so 0x7ff, then we have 2 bytes. And okay, so what do we have here? 7ff has so these two are 8 bits, and with this, okay, so it's 12 bits. And here we have 1 2 3 4 5 6 1 2 3 4 5 11 bits. Okay, yeah, it's 11 bits because it's 7, it's not f. If this was an F, then it would have been 12 bits, but it's 11 bits. And how do we store this? Which character should be the upper and the lower? Is this in Little Indian or Big Indian? Okay, here we go. Okay, let's look it up online. So code point to UTF-8. Okay, so let's say that we have code, I don't know, FF0, FAT80, or I don't know, something that's more easily recognizable. EF0. Okay, that's not helping. Does anyone say how these are supposed to be? One continuation byte. I don't see it mentioned anywhere. Are we supposed to use little endian or big endian? Okay, so start from the right. So from the right we have 0, 1 and a lot of ones. Then we have this 0, 0, 0, 1, 1, 1. And then 0, 0, 1. Okay, so it is in big endian essentially. Writing to FAT32 drives, yeah, I will do it, but later after doing the VFS and all that. So I'm doing it in the kernel. Writing. Okay, so essentially it is in big endian. That's kind of what I was trying to figure out here. What this means is that the higher bits go into the left. So here we have the upper 5 bits. Okay, so this is the form we have here, right? So the upper 5 bits will go into the first byte, and the lower 6 bits will go into the second byte. So this would be... Okay, let's see what this number is. So 110. Okay, so this would be... Okay, if we put 1, 1, okay, that would be C0. So this would be C0 ORed with the upper 5 bits. So basically it is the code point shifted to the right by 6 positions as we have here. And let's also mask it so we only get 5 bits. And to get 5 bits, the mask should be, let's see, 1, 2, 3, 4, 5, 1F. Alright, this would be the first character. Okay, this is gonna be annoying if I don't use it like this. And the second byte is 10, so this one is an 8. And then the next 6 bytes, so this will be a 3, and the code point and okay, like this. Okay, then we have the next range, which is up till FFFF. And in this range we have 3 bytes, which is even gonna be even more fun. Okay, so here we have 3 ones, and 3 ones is maybe E, I think. 1 1 1 E0. So E0, and then we take just 4 bytes, so this is just gonna be F. And then we need to shift everything by, here we have 6, and here we have another 6, so we have to shift everything by 12. Okay. Then the next byte, which is this one, it has an 8 at the top. And then it has 6 bytes, 6 bits. So this shifted to the right by 6 and 3F. And then the last byte is also with an 8 at the top. And then we take the last remaining 6 bits. Does this make sense so far? It's not pretty, but you know, what do you want? This is UTF-8. Code point is smaller than okay, and finally we have 4 bytes. And for the 4 bytes, the first one is an F. That's 4 ones is an F. And the second one is only 3 bits, which is 7. 1 1 1 is 7. Okay, and we have 6 times 3, so that would be 18 bytes here. And then it's kind of the same as we had this one, except that it's an 8 and we have 6 bytes, so here we have 3F. Alright, so this is an F, and then we add the code point shifted to the right by 18 and 7, so we get only the 3 bits. Then we have the next 6 bits with an 8 in front. Alright, and then the next, and then the final bit, and that's it. Else, something is wrong, and okay, now we have to return this string output. If the code point is higher than this number, then it's not valid, so we can ignore it. But I think something, should it be smaller than or equal? Yes, it's smaller or equal. Yes, everywhere. Alright, and if the code point is larger than this, then it's probably not valid, so we can just ignore it. Thank you, happy coding. Okay, this function is not pretty, but I mean, this is what we have to do here for processing Unicode. Okay, so now we have to go into FAT.c, and here we have this there was that function which searched for entries. Okay, it's this one, fat find file. And what we are doing here, we are trying to convert this name to a short name. So this is exactly what's happening here. Okay, so let's call this short name. And I'm going to create a separate function for this. I think that is for the best. Get short name, file name, and then char short name of 12 characters. And here, well, I'm just going to move all this code. And instead of fat name, the name is short name. And we can leave this name so we don't have to. Okay. Okay, this is a pointer, so even though we specify the size here, this is not gonna work, so we have to hard code it to 12. All right. Okay, and okay, so this is basically the function which gets the short name. Now, I think in this read entry, we should be looking for the VFAT entries as well, but let's see how these are laid out in the file, because that is the biggest question. FAT. Okay, and the long file name entries are always placed immediately before their 8.3 entry. Here is the format of a long file name entry. And first we have the order in the sequence of long file name characters. All right. And in each of these long file name buffer, basically, in each of these. So basically what we have here is 32 bytes. Now, out of these 32 bytes, we have 5 plus 6 plus 2 characters. So in each of this long file name entry, we can have up to 8 plus 5 is 13 characters, which are stored in UTF-16. All right, so I think this read entry function should be reading these is this one used anywhere else? No. Okay, so this function is only used here in find file. So I think it'll be okay to make that here. So if this entry dot attributes, because that's where we can find this stuff, and I think I'm okay. This is the long file name attributes. This is what we need to check for. So if this is a long file name, then we need to start building one of these long file names. Now, something that to keep in mind here is in Windows by default, a file name cannot be larger than 256 characters, a long file name that is. And I think we can use that here. So what this means is that, so we have 13 characters in each of these long file names. Hold on a second. Did I look at exFAT again? Yeah, that's okay, because it's basically identical. All right. And I'm reading here to see. Okay, so the first byte the order of this entry in the sequence of long file name entries. So this is a 41. So what does that mean? First, the 1 tells us that this is the first file name entry for the regular 8.3 entry. Second, the 40 part tells us that this is also the last long file name entry. All right, so that 40 is how we can tell that this is the last one of the long file name entries. Okay. So in that case, what we can do is do if entry dot. Okay, so we need to see what is the first. Okay, so in regular files, we had the file name. Okay, so we basically need to use a different structure for these entries. All right. So let's call this a long file entry. And first we have the order. Okay, I'm gonna copy this table. All right, so the order. And let's also define a constant for that last. So fat order, fat LFN last is a 40. Okay, and then we have the attribute, which is uint8. Hold on, no. Okay, and then we have the first the first 5 characters. So let's just use int16 for this. Chars 1 of 5. So then we have the attribute, then the long entry type, checksum, the short file name can change without changing the long file name in cases when the partition is mounted on a system which does not support long file names. Oh, okay, so what this means is that if the file name is changed, then this checksum will not match, and we should not read it if the checksum doesn't match. Okay, that makes sense. Then we have the next 6 characters. Then we have 2 bytes which are always 0, so uint8, uint16t always 0. Okay, and then the final 2 bytes. So okay, this is what a long file entry looks like. All right, and now we will just cast this entry to a long file entry, and now we can access all the long file entry attributes. Okay. Now, okay, so we know that 40 is the limit for okay, and 40 means that we can use 1, 2, 3, 4, 5, 6 bits. So we can use 6 bits for the long file name, basically. Okay, so what this means is we can have up to 63 times 11 characters. 13, sorry. Yeah, that should have been in decimal. So we can have 819 characters. What the hell is it doing? I hate this calculator so much. It's so hard to use. So it's 819 bytes in theory. Characters, not bytes. So in theory, we could have up to 819 bytes. But I think in practice, the 256 byte character limit is still in place. But in any case, we can allocate 819 without a problem, so... Alright, let's use this data section I have here to allocate some memory. And what we need here is to basically use that order in order to sort all the characters, which is unpleasant. You have to do some sorting. Alright, so... Okay, I don't want to create two structures here, so I'm just going to create a single structure. I'm just going to create two arrays. So the first array will be of FAT LFN order of 63 is the max, so let's just use... actually, I have that LFN lost. That is just perfect. And then let's use white char. Okay, so the idea here is that I will store in this array all the entries as I'm getting them, and whenever I encounter one that has this last one, I will just convert everything at once to a normal string. All right. And we should also keep a count here, so int FAT LFN count, which should be initialized to 0. That would be a good idea. So in here, gdata. All right. Okay, so whenever we get one of these LFN long file names, we'd first check if it... Okay, so we just copy it first. Let's copy it. Let's start by copying. So, data of LFN order of count will be equal to LFN order, and let's have a mask here, so that last one minus 1. That is perfect. So what I'm doing here is, so this is 40, so 3F would be basically a mask which would only have all the bits which are on the right hand side of this 4 basically. So where's my... I've closed the calculator because it annoyed me. Okay, you get the idea. So that's what the mask is for. All right, and then gdata, and then we want to copy the data. So we're just gonna use memcopy. Actually, for consistency's sake, let's use uint16 here as well. Int16, that's fine. Okay, so let's copy to gdata FAT11 characters of gdata. Okay, that's too much to write. So let's have like int index equals this. That we will just increment. Too much to write otherwise. Okay, so we are copying to the beginning. We are copying the first 5 characters. So LFN chars 1, which is the first 5 characters, but these are 2 bytes each, so it's 5 times 2. And then we have 2 more regions from chars 2, which is 6 characters. Actually, I think we could just use the size of. All right, and we have to add this as the offset. So, okay, let's also have another offset equals 0. Okay, actually, I don't think this is necessary. So this would be chars 1, which is 5 plus 5, because these are due in 16s, yes. And this one would be plus 5 plus 6, which would be 11. Okay, so we have copied the data over to this LFN characters. And now let's check if it's the last one. So, is this the last LFN character? LFL block or whatever. So if LFN order has the FAT LFN last, it's different than 0. Then we basically need to sort these blocks, which is gonna be very annoying. Okay. Now, I'm not gonna sort them. I'm just gonna have like a selection algorithm which selects the smallest value until I select all of them. Okay, but that will not be very efficient. Damn it, I hate this so much. Is there a quick sort algorithm that I can just copy and paste? Alright, this is the glibc, but glibc is usually very messy and has a lot of stuff, so let's try to find a simpler option. Okay, this is from the Linux source code. No, it's from glibc as well. Implementation on GitHub. Quick sort as a C macro, really? And I'm also looking at the license because I don't want this to be... I want it to be MIT or something very permissive, since my code is basically public domain. There are some implementations, but I don't see anyone which... Oh, come on, do I really have to do a quicksort implementation here? C program for quicksort. And he doesn't have a license as usual. Okay. Yeah, I think this might be the one. There's just one exception. It's not using that stuff from the standard library. Stable queues, quick sort. Oh, damn it. It's using allocations and stuff. I'm not having fun with this. Yeah, I'll have to do my own quicksort implementation, which I'm gonna hate, but whatever. Ah, fine. So the qsort in the standard library is in stdlib, I think. All right. So let's create an stdlib here. And stdlib.h, and the way the pragma ones. So the way the quicksort looks like in C is like this. So okay, let me just see a reference. Okay, so it's void qsort, and we have a pointer which points to where the array begins, but and then we have the number of elements in the array, and then we have the size of elements of each element in the array, and then we have a comparison function, a compare function, which takes in two const voids. So it's basically the pointers to the elements. Okay. And the way this works is by using a pivot, and I'm gonna have to do like a internal version, which which takes in all of those things, but it also takes a left and a right. Actually, I think the qsort might not be recursive, so this one. Okay, I'm trying to find one which isn't recursive. Let's see if I find one. Yeah, so all the implementations are recursive, it looks like. I can't find anyone which is not. Anyway, whatever. Let's just use one which... It doesn't really matter that much. Okay, and for this internal function, we will also need a left and a right. So size t left, right. And basically if left is greater or equal to right, return. Okay. Pivot will be okay, so we are using the left value as the pivot. And let's see what number. Okay, so this would be base plus I multiplied by the size of an element, which would be size. All right, and now we need to see what trying to understand what this code does, and I found something very weird. So here they're taking target of I, which is this, and then they have this loop. So while target of I, which is equal, okay, this makes sense, because this is in a for loop. So the first time it doesn't make any sense. This one will just exit immediately. And then while pivot is smaller than target of J, so J is on the right side, we're trying to shrink that right side. Okay, and this is where they swap. Okay, this makes sense. Okay, I'm gonna implement this code. Okay, implementing quicksort is not that fun, I'm telling you. Okay, so here we need to obtain... we need to use that comparison function. Compare... And we need to compare. On the left side we have base plus J multiplied by size. So while this is smaller than 0, I plus plus, and then while the pivot, so okay, so we're comparing this to the pivot, and then while the comparison between the pivot and target, okay, so that would be base plus J times size. Okay, this one was I times size, sorry. And this one is J times size is smaller than 0, then J minus minus. If I is greater or equal than J, we need to break and then swap. And that's... annoying. Okay, so we basically have to swap byte by byte or something like that. Because we don't have any extra memory. I mean, we don't know what the size could be. It could be 1,000 or it could be 10,000. So what we're gonna do is just swap byte by byte. This sort will not be super fast because of that. But yeah, whatever. So for int, okay, so I and j are used, so let's just use k equals 0, k smaller than size, k plus plus, and we need to assign whatever is in base plus I times size, and we want to convert that to a byte. Okay, and to that byte we add k. My god, this code is so ugly. And then this will be equal to this. And then I'm sorry guys. So I'm putting from I to temp, then hold on. Okay, j to I, and then temp to j. I hope it works. I have no idea. I honestly don't know. I hate this code so much. All right, but what's the pivot? I'm not sure if this quicksort implementation is good because it looks weird. So for the pivot, I would expect it to take like, I don't know, a third of the way or something like that. But here, it's taking the pivot as just the item on the left. Although that might not matter. I don't know, we'll see if this works or not. We do have to test this, obviously. Because it's so ugly. I'm not proud of this quicksort implementation. Alright, and after doing this swap, we do I++ and j minus. And finally we call quicksort, so q sort internal, base number num, size, and then for the left we use left, and for the right we use I minus 1, then the comparison function. And then we do the same, but this time for j plus 1 and the right side. And initially we need to call it with base num and the number of elements. Yes, so size, and then the left will be 0 and the right will be number minus 1. So the size of the array minus 1, and then the comparison function. Alright. I think I need, for the size t, I need std_def. Oh, and yeah, I should move this to the C file. set to stdlib.h. All right, and let's also move this qsort function, and we're just gonna leave the declaration. All right. Okay, I'm gonna do this here in main. I have no idea what's gonna happen because... Okay, hopefully nothing bad. Let's see. You know what? It might actually be a good idea to test this implementation on the host. It's fine. It's fine. We're gonna test it in production, in the OS directly. Okay. Int my array. Let's put some random numbers in here. Okay, this is not Python. Sorry. Equals like this. And then let's implement that comparison function. So int my compare const void a, const void b, and this will basically return a pointer to the address where that number is, and we need to... Okay. So a is that a pointer costs to an int pointer and then dereferenced. Same for b, and return a int minus b int. Okay, and include stdlib moment of truth. So okay, let's just do it here at the beginning. Let's try to sort this my array, size of my array divided by the size of int, whatever, that's fine. Then the size of one element is size of int, and then the comparison function is my compare. And then let's see if this works. So for I equals 0, I smaller than whatever this is, I plus plus, and let's print the number of my array of I. And at the end, we'll print a new line. Okay, so what do you say? Will we see a sorted list or not? Okay, known type wchart. Yeah, so that might not work. Alright, so let's just use the int16. I think that's the easiest solution. I'm not sure in what header. Oh, it's in std-def. Okay, that might work. std-def. Let's see if that works. Okay, that seems to have worked, but we have some errors here in std. Unknown type uint8. Oh, stdint.h. Okay. We still have an error, so temp is undeclared because okay, so okay, string.c. Okay, so I did some a mistake here. As I was saying, I would like to return this string, so let's do that. Return string, and then the code point, we will just place that into this number here. So code point equals c1, and here and here. Okay, it's basically this. Okay. Let's see. And here we go. Oh yeah, the numbers are sorted. Oh yeah. Even though I wrote the ugliest printf function I could have ever, the ugliest quicksort function I could have ever written, it seems to work. That's great. All right, let's do the same and see if we can sort something more complicated, like some strings. Let's try that. Main. Okay, so this time we'll use a const char array, which will have some random strings. And they should not be sorted, so all right, I think that should work. And instead of ints, now they are const char arrays. And instead of doing this, we have to return string compare of A and B. I'm not gonna bother to rename those. And we need string.h for that. Okay, and here instead of size of int, it's size of a const char pointer. So it's easier to just do my array of 0 here. Same here. And each one is gonna be a string. Okay, let's see if we can sort some strings. All right, we have some errors. Do I not have string compare? That might be the issue. I don't have string compare. Who would have thought? All right. So let's implement string compare then. Now the implementation of this is quite simple. We basically... Okay, so if A equals null and B equals null, then we'll just return 0. Okay, if one of them is null, does that even make sense? Let's see, does this even make sense? Behavior is undefined, so okay, we'll just use... Okay, so if A is null or B is null, then we'll just return -1 or something. So they're not equal, but one of them is null and the other one is not. All right, and now we have to look at the characters. Okay, so while A and B, okay, so while A is valid and B is also valid, and A is equal to B, then we advance A and B. So as long as these two are valid and equal, we are going to increment them, and then we will just return I minus b. Okay, this is what string compare looks like. All right. Let's see. Okay, there was some warning here. Okay, whatever. Nobody cares about those errors. Oh, I actually, hold on a second. I think there might be an issue here. Okay, so this is an array of strings, right? And this one will give me the pointer. It will not... Okay, so this one will give me a pointer to the pointer which points to the string. So this is a double reference here. And this is what I got wrong. And I think I should fix that. All right. There we go. So it's a double pointer. All right. Let's see if those strings are sorted. AAA, Alpha, CCC, hello. Okay, nice. This is very beautiful. So it does look like this works. I did not expect it to work. Let's try it with something a bit more complex. Let's try it with maybe some structure. So let's have struct my... Okay. Type def, struct my struct. So let's have something more complicated. Let's have like an int, a and, I don't know, int number, and maybe we have some... Okay, let's just put another string. A string. Okay, and now this array, let's make it of these structures. And let's also add some numbers here. Okay. And I also need to close these. Okay, and now for the compare function, what we're gonna do is, so these will return pointers to one of these. Okay, so let's just call these AA and BB, and we're not gonna dereference them this time. And all right, and what we want to return, okay, so let's sort by the string first. Okay, I'm gonna call this my compare string. And then let's do another one which compares by number. And this one will return number minus BB number. Okay, and so let's call this function twice, once with the number and once with the string. And each time we will print both of these. All right, dot number, and then my array of I dot string. And we will call this twice. Okay, let's see this in action. Okay, so first time we sorted by the number 1, 2, 5, 7, 32, 55. It works. And the second time by the string. Okay, so we have a sorting function. Great. That seems to work. I don't 100% trust it, but okay, let's say it works. Okay then. Let's go back to that FAT.c. And in that case, we will have to use a structure here that might, so that we can sort it by that order number. Okay, so struct fat elephant block, and this block will have 13 characters, because that's how many. So these are uint16s. Okay, so they are white chars characters. Okay, I'll just call it chars. Less stuff to write. And then on uint8 for the order. Okay, and then we need a comparison function for these blocks. Okay, and let's create one here, should be fine. Okay, and now we need to cast this to the right data type. Same for the second one. Yeah, the asterisk is here. And then we will return order, and let's just convert that to an int so that we can have negative numbers. Because the order is uint8 and we also want to have negative numbers here when we compare them. Alright, and now instead of having in this data region, instead of having 2 arrays, we will just have 1. And let's just call this elephant blocks. And then this one will be an elephant count. All right. Now let's modify this. Okay, and now I am changing these to use that chars that I created. All right, and now we should be okay. Okay, so if this is the last elephant block, we'll have to call qsort. Let's include std lib. All right, and we are sorting this elephant blocks array. The number of elements in the array is this count, so gdata elephant count. The size of an element in the array is the size of one of these blocks, so size of fat elephant block. And the comparison function is that fat compare LFN blocks. Okay, and now they are sorted. That's great. So what we have to do next is we have to basically, okay, so let's call this the short name. And let's also declare another char for the long name. And this one will be 256 characters, and we will not accept any more than that. Okay, so now we will iterate over each of these blocks. So for I equals 0, I is smaller than this LFN count. All right, and for int j equals 0, j, and then g data LFN blocks of I dot chars of j is different than 0, because when we get to 0, then we've ended the string. And j is smaller than 13 and j++. Okay, and then we extract the code point, so int code point, and then we have that function in string.h. Okay, I already have string.h. Alright, UTF-816 to code point, and the string is this one. Okay, plus j. Okay. I need to do this in a bit of a different way, so okay, so let's take an int16 pointers to chars, and which is equal to this long thing. And let's do a while loop instead. So while char, okay, so okay, let's set the chars limit to chars plus 13. So we don't want to go above that. So while chars is not 0, and okay, so first we should check the limit. So while chars is smaller than chars limit, and chars is not 0, so we haven't reached the null character. Okay, we're gonna extract the code point, and chars equals UTF-16 to code point. Okay, so this one will basically modify this chars to be advanced by 1 or 2 or however many characters it has to. Okay. Chars is the string, and the code point is code point. Okay, and we also need here we need char name position will be equal to name to the long name or whatever, and then we will do the reverse. So name pos equals UTF code point to UTF-8 of code point, and then this string here. Okay, now I haven't checked if this goes above this 256, but it's something we should do at some point, but I'm not gonna do it right now. I'm really curious if this works. It looks ugly, it's messy, it's... Okay, let's print this. fprintf, long file name, and then the string. Yeah, so the last characters we should set to 0 to make sure that to make sure that printf works. Okay, and let's print the long name. Okay, moment of truth. Okay, we've got some warnings here. Okay, so I'm passing on int16 instead of wchar, but I think that's fine. Okay, and nothing. Okay, we tried. Yeah, I'm not really sure what's happening here. I need to do some debugging, and I think it might be a very good idea to move the code to the host. So to basically, I had this in tools FAT16, just move this code there and try to debug and see where I have gone wrong. Now I've been streaming for almost 4 hours and it's a bit much for me, so I will call it here. Okay, so I will post this code. I will upload this. I will put this code on GitHub, but I will just disable it. So I'm just gonna comment it so it's not called. If that sounds good to you. Yes, I should update the README. You are correct, because in addition to these dependencies, there's also Python 3 scons, and maybe there are some others that I can't remember. Or now these. And it's not make, but scons toolchain, and then scons. Use scons run to run the test. Okay, is there anything else about make? We still need make because okay. We still need make because the toolchain build uses make, so we still need it. Okay, so updated readme with new build instructions, and then I will post the rest of the code with the exception of having it commented here in FAT.c. And yeah, maybe in the next okay, maybe in the next live stream we'll take care of it. Okay, so all the way from here to here, I'm gonna leave it commented. So this code will not run, and also this. Okay, everything should work fine. If we run this, there shouldn't be any errors, any warnings, any problems. Okay, if there are any questions, now is the time for questions. If there are any questions about everything I did today, about anything related to operating systems in general, about anything that you want. Yes, this works. Perfect. So let's commit. Not this. This is the wrong code. Oh, come on. Did I? No. Okay. Okay, work in progress. Attempted to add support for long file names in FAT driver. Okay. Okay, okay guys, if you have any questions, I'm hearing. If not, then we will end this stream, and thank you a lot for watching. I hope this was useful for you. You learned interesting things. Yeah, we have a FAT32 driver which works, which is great. We can boot from hard drives, which is very good. The long file name support is a bit more complex. It needed quite a lot of work, more than I anticipated, like sorting by that order and whatever else. Yeah, so that was a lot of work. And yeah, maybe I will test in the next live stream, or I will think about what I will do in the next live stream. Yeah, that's basically it. I am using Fedora with the default GNOME environment, but I do have some custom themes going on here. So if I go to tweaks, you can see that I have the theme, this one. So this is the icon theme, Orch is Dark is the shell theme, and for the applications. And yeah, it's GNOME. I'm not the biggest fan of GNOME, but it works a bit better than... Oh, sorry. I always forget about this. Okay, so I wanted to show here in tweaks. These are the settings I have. So the icon theme is Stella Purple Dark. Shell is Orc is Dark. And that's it. And I do have a lot of extensions. Here's my list. If you want to know, I'll just move my head so you can see this list better. Okay. Here's the list of the ones that have the dot are active. The rest are not. So these are the... if that's what you want to know. Okay. Any other questions? If not, then thank you very much. I hope this was useful for you and you learned a lot of things. Yeah, I agree, there are a lot of extensions. But I think they're very useful, at least some of them. I still want to have like the legacy icons, which for some reason are removed. I still want to have this menu because I prefer it. But I mean, this one is pretty nice too. Don't get me wrong. Yeah, there's a lot of stuff here. There's this blur, which I really love how it looks. Looks very nice. Okay. Alright, I don't see any more questions. In that case, thank you and see you the next time. And yeah, the next time will probably be in 2 weeks. I will announce it, you know, a few days before, so you know for sure when the day will be. So until then, thank you very much and see you next time. Goodbye.